A brisk and early morning to you from the east coast of New Zealand as we count down to our next Electron launch from LC-1. Bit of a foggy one today, but there on Pad B stands our 91st Electron rocket, ready to carry its 10th dedicated mission to LEO for Japan-based Earth observation company Synspective. We're about 20 minutes into the countdown to liftoff, set today for 5:43 a.m. local time. My name's Julian Spice, along with Grace and Leslie. We're joining you from Rocket Lab's Mission Control Center right here in Auckland.
Thanks, Julian. It's been a clear run through the early morning operations, and we're tracking no issues across the launch vehicle, Synspective's payload, or the range, which sets us up nicely for an on-time launch. One thing we are keeping an eye on is the weather, which is a bit unsettled and could impact the launch. We'll find out closer towards T0. Otherwise, it's onward to launch for 10 out of 10. We're heading to a 552-kilometer low Earth orbit today with this mission called 10 out of 10 to mark our 10th constellation launch for Synspective for their Earth observation service, with Strix being the name of their satellites, as well as the genus for owls. You can see where the name comes from.
What a hoot. And I mean, the pun opportunities are endless, which is actually a good thing because we've got another 17 Synspective missions to name after this one to fit the owl theme. These missions are to establish Synspective's Strix constellation with SAR satellites by the end of this decade. In case you didn't know, SAR is a type of image capture technique which stands for synthetic aperture radar. This technology bounces radio waves off of landscapes and objects. Measurements of those radio waves are then stitched together to create imagery for use across industries like urban development, construction and infrastructure monitoring, and disaster response. Here's more from our friends at Synspective.
Synspective's mission is to create a new infrastructure that enables the next generation to understand our Earth scientifically, quantitatively, and achieve a resilient future.
Liftoff.
All right, I just want to be clear. I did not write these, but we've got a few owl puns that we came up with during that clip if you want to hear them.
Yeah, okay, go on.
I'll never let you go. You're owl I need. Owl, yeah.
All right, add them to the list, but maybe don't give up your day job.
I don't think either of us have a career in comedy anytime soon, so I don't really have a problem with that. Okay, T-minus 17 minutes on the clock, and I think now is a great time to fill you in on our latest acquisition here at Rocket Lab. We've added robotic arms and other very cool tech to our lineup of hardware and capabilities. This technology is used for missions happening at Mars right now.
If you've ever seen photos of NASA's Perseverance rover searching for signs of past life on Mars, the technology that makes up that exact robotic arm is now under the same roof here at the lab. That makes us one of only a few companies in the world capable of delivering Mars missions across the entire spectrum. That's launch, spacecraft, software, and now Mars-proven robotics for surface and on-orbit operations. Here's more about the company and the technology that's joining us here at Rocket Lab.
The robotics that we brought on board here are going to enable not just missions, but a whole new diversified portfolio of components to proliferate into our spacecraft.
From a big picture perspective, Motive is bringing into the Rocket Lab family a number of capabilities that really solidify the vertical integration of an end-to-end space company. Some of those are simple, solar array drives and gimbals and things for positioning on orbit. Others, we move into the optomechanical side with filter wheels and focus mechanisms, also for imaging the Earth and other applications like that. And then finally, the robotics side, where we can lend a huge support for things like exploration robotics, whether that's the moon or Mars, or on-orbit servicing, or even national security.
Bringing these robotics in-house really strengthens our ability to go after these really complicated missions. Missions to the moon, as we know, there's tremendous excitement and growth in the moon industry right now. Mars is always a very important planet that needs a lot of programs still yet to go. And then we think about what's going on throughout our solar system. Rocket Lab has always had a soft spot for these interplanetary missions, whether it's Venus or Mars or the moon. We always have an involvement in them somehow. And this is core robotics. And if you think about space, space has really been defined over the last sort of half century with robotic missions.
Obviously, we come from a background of doing Mars missions, so we're very excited about, Mars sample return and activities like that, where we can really start to expand on what's been done successfully and then build a future there that's also a little more permanent. On the orbital side, we have national security things. Obviously, we're doing a bunch of servicing activities for servicing spacecraft, refueling, repositioning. All those things require robotics, and that's really starting to ramp up right now. So almost in every one of these areas, we're seeing an inflection point with growth going all over the place. So it's really exciting to be able to have Rocket Lab be a partner and scale what we're doing in that area.
We're really excited about the possibility of Rocket Lab robotics and the scale that we can bring as a wider organisation to it. And I think this is one of the exciting things about when Rocket Lab acquires a company, is we're able to put the full Rocket Lab force and might behind those companies.
We have 12 years of building really advanced technology, unique in the industry. And Rocket Lab brings in a proven track record of being able to take that and then scale that up. That will really enable the growth of this site and overall the Rocket Lab Robotics brand within the Rocket Lab family.
It's super exciting to have the Motive team joining us. With those robotic capabilities on board, we're in a great position to lead on exciting major missions, like bringing samples back from Mars, helping build NASA's Mars Communications Network, known as MTN, and tackling other important deep space exploration projects and national security needs.
So cool. Looking at the clock, we're coming up on the final go, no go poll for today's mission. Run out of Mission Control Center by Launch Director Michael Pearson. They'll be checking in with each one of our operators across the consoles here and at the range to make sure there are no critical flags preventing us from moving forward with today's launch attempt. If something does need attention, they'll respond with a no-go and further info. Otherwise, we're listening out for a clean sweep of goes from MCC, starting at T-minus 12 minutes on the clock. So let's listen in now.
All stations LD on mission, proceeding with the go, no-go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
VCon.
VCon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
FAN.
FAN is go.
LSO.
LSO is go.
And LD sub.
LD sub is go.
Okay, the go, no-go sequence is complete. We are T-minus 11 minutes, 11 seconds, and counting. We're go for terminal count auto sequence at T-minus 10 minutes. From this time, the 3-word procedure is in effect.
That's exactly what we wanted to hear out of MCC. We are go to proceed towards Electron's launch at 5:43 a.m. local time here in New Zealand, or 2:43 a.m. in Japan for this inspective team.
Today's mission includes rocket number 91, but our most recent mission on Electron's 90th launch was something pretty special. About a week ago, we deployed the Victus Haze mission for the U.S. Space Force from this very same launch site. The mission was a test to see if we could go from call up to launch in a single day. And if you know anything about Rocket Lab by now, you'll know that we took that challenge to heart and smashed out a new record in responsive space for the DLW. 16 hours and 42 minutes. That's all the time it took to go from phone call to liftoff for Victus Haze. Let's take a look back at the highlights.
LD, this is MD on mission.
MD-LD.
We are go for vertical.
LD, GC mission cord. GC-LD. ECS disabled, hold down mechanisms armed, pad auto sequence armed, pad ready for launch. Launch load is complete, system is in recirculation.
Victus Haze is configured for ascent state and ready for hot pursuit.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff. Vehicle has cleared the pad. Beginning pitch over.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
Payload separation confirmed.
Nominal transfer orbit achieved. MD-LD on mission cord.
Go ahead, LD.
Spacecraft separation is confirmed. Victus Haze is all yours.
Copy, LD. Space Systems is taking control. Thanks for the ride.
Victus Haze is the first launch plus spacecraft mission we've deployed for the US Space Force, which is very exciting stuff. And much like how we launched in record time, we completed checkouts for our spacecraft hours ahead of schedule too. From launch to completed spacecraft commissioning took just 38 hours, more than 33 hours ahead of the mission's 72-hour deadline. Check out some of these cool views from LEO from Pioneer's mission assurance cameras. Since then, Pioneer has completed its first rendezvous maneuvers for the mission, which involved getting up close and taking images of a second spacecraft. A bit like a high-stakes game of orbital cat and mouse. Those 24/7 ops continue to Pioneer and our operations team, so make sure to check out our website and social pages for more cool photos and videos about Victus Haze. All right, with terminal checks complete and launch pad ready underway, we are at T-minus 7 minutes and counting. Shortly, we'll see the top clamp open and strong back retract in preparation for flight.
Now, the vehicle taking Synspective to orbit today is the Electron rocket, standing 18 meters tall on the pad. Electron is a two-stage rocket with a kick stage made dedicated to launches for small satellites across commercial, civil, and national security missions. Coming in at 13,000 kilograms once fully fueled, Electron sits in the small lift class of orbital rockets and has been the world's most frequently launched rocket of its type for many years now. Today's mission is launch number 91 for Electron, and we're expecting to hit launch number 100 in the next few months.
From the top of the rocket, we have Electron's protective fairing over the top of the Strix satellite for today's mission. From this angle, you can see that this nose cone is not our usual standard fairing. This one has been customized to accommodate the boxy shape of the Strix satellite without compromising on aerodynamic performance. And it's a customization we've rolled out for a lot of our Synspective launches to date. Once we're in space, the fairing's two halves will separate to clear the way for the latest StrixSat to be released. We use carbon composite material across the fairing and the rest of the rocket below it, which is what gives Electron its unique black appearance. Carbon composite gives Electron an exceptional strength-to-weight ratio that's strong enough to handle the forces of launching through Earth's atmosphere, whilst keeping the overall structural mass low enough to maximize payload capacity on a small rocket.
That's right, and Electron's second and first stages below the fairing carry the same propulsion system powered by our 3D printed Rutherford engines. The second stage contains a single Rutherford engine with a larger nozzle made for the vacuum of space, while the first stage includes 9 of those same engines. What makes Rutherford special is that it's the world's first battery-powered 3D printed rocket engine. It's an electric, pump-fed cycle engine that uses batteries to power the motors that drive the propellant pumps. And unlike open-cycle gas generator engines, which burn a small amount of propellant to power the turbopump, the Rutherford decouples its pumps from the combustion process, which means we don't waste any propellant to run the Rutherford and operate at a 95% efficiency. And because they're 3D printed, they're relatively quick to make. It only takes around 24 hours to 3D print the thrust chamber, injector pumps, main propellant valves, and any other parts we need for a Rutherford engine.
In fact, all the engines on Electron are 3D printed, even the tiny engine we have on the kick stage. That engine is called Curie, and it's capable of multiple relights on orbit to be able to maneuver the kick stage for plane changes, altitude adjustments, or multi-manifest missions where we're deploying satellites to multiple locations. Our capability is especially useful for constellation deployment missions like today's, which allow our customers to deploy their satellites exactly where they need to be. And so for the 91st time, we are nearly ready to head to orbit again.
That's right, we've got just a couple of minutes left before liftoff, and soon at the T-minus 2 minute mark, our operators hand over control to the rocket's flight computer to take us through to T0. This is called the autonomous auto-sequence start, and from this point onward, the rocket is essentially making its own go-no-go decisions based on hundreds of sensor readings across the vehicle. One of its first actions is to arm Electron's AFTS, or Autonomous Flight Termination System. This is the system with control over Electron's launch corridor, and it will be monitoring the rocket's trajectory and flight health for any intervention if needed, if things go wrong.
And at the same time, Electron's propellant tanks across Stage 1 and Stage 2 are brought up to their final flight pressure levels. That's a call-out you'll hear within the T-minus 1 minute mark. This pressurization is critical because it not only forces propellant into the Rutherford engines when we need it to, but it also provides strength to the tanks during flight, similar to air pressure inside of a balloon. After that, it's on to another 2 call-outs from the launch director, one at T-minus 20 seconds and another at T-minus 10 seconds to mark the final countdown to liftoff. These are the last manual checkpoints before Electron commits to flight right at T0. That auto-sequence start is moments away, so we're going to hand it over to Mission Control now and listen in to the final countdown. Go Electron, go Synspective, and go Strix.
The vehicle is fully on internal power. AFTS is green and enabled for flight.
ECS is disabled. Box load is complete. System is in recirculation. Anti-geyser is disabled. Stage 1 and 2 tanks are pressed for flight. High flow engine purge enabled.
T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Beginning picture.
Stage 1 propulsion nominal.
Tens across the board with Electron's launch off the pad for Synspective's 10 out of 10 mission from LC1. We're now 42 seconds into flight and approaching our first critical milestone, max Q, or maximum aerodynamic pressure. This is the point where Electron experiences peak aerodynamic loading on its way through Earth's atmosphere and on the way to space. Let's listen in now for confirmation from Mission Control that we've cleared max Q.
Electron is supersonic, approaching max Q. HVB discharge holding nominal. Cleared max Q.
And there's the call. Max Q is behind us as Electron continues its way onward to low Earth orbit for Synspective. Electron is now more than 20 kilometers above Earth and traveling at more than 2,500 kilometers an hour, thanks to the thrust coming out of those 9 Rutherford engines at the bottom of the first stage. Coming up shortly will be a rapid sequence of events for Electron. Main engine cutoff, followed by first and second stage separation, and then second stage Rutherford ignition.
First up with main engine cutoff, or MECO, those engines will shut down simultaneously to slow the velocity of Electron just a touch. This very brief coast lowers the dynamic forces at play for stage separation when the second stage is separated from the first stage. That separation event creates a bit of distance over the couple of seconds before the Rutherford engine on stage 2 lights up to continue on with the mission. Let's watch and listen now.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
Beautiful execution there by Electron with a nice clean MECO, stage sep, and nominal second stage engine start. Very soon we're expecting fairing separation when Electron's nose cone splits and falls away to expose the Strix satellite to space for the very first time. Let's watch this together. You should be able to see the jettison happen on your screen.
Fairing jettison confirmed.
Fairing jettison confirmed, and you're looking at Synspective's Strix satellite attached there to Electron's kick stage, ascending closer towards its operational orbit at 552 kilometers above Earth.
Believe it or not, each one of those fairing halves weighs less than 50 kilograms thanks to its carbon composite construction. Light enough for a single person to move around on their own, though they'd have a bit of difficulty at the speed Electron is moving right now. More than 8,300 kilometers an hour at climbing more than 141 kilometers above Earth. The second stage will continue on that way for just under 6 minutes longer until it's time to separate the kick stage and Strix satellite into orbit.
Stage 2 propulsion holding nominal.
T plus 4 minutes 30 seconds into the mission now, which means we're about halfway through the burn time of this Rutherford engine on Electron's second stage. Because the runtime for this engine is a lot longer than what it took on the first stage, the batteries powering the motors that drive Electron's electric pumps are draining close to depletion, but we still need batteries to keep the engine running. So what we do next is perform something called the battery hot swap. We essentially disconnect and get rid of the old battery packs that are literal dead weight for the vehicle and connect over to a fresh battery pack that will keep the engine firing all the way through to our next stage separation event. It's the silver battery packs on the right that will fall away, so let's keep a close eye on the screen here to see that moment in real time.
Guidance is nominal, 200 seconds remaining. Throttling down. HVB discharge holding nominal, approaching hot swap in roughly 30 seconds.
Battery jettison confirmed.
Hot swap successful.
Hot swap confirmed, and that's a nice continuous burn coming from the stage 2 engine there with that maneuver complete. We've got another 3 minutes or so until the second stage's final actions for this mission, which will be to separate the kick stage with its strict satellite and set it on a course for payload deployment within the hour.
HVB discharge holding nominal.
T plus 7 minutes and 17 seconds on the clock. Electron's second stage is firing beautifully as we expect. Still a couple more minutes to go for this phase of the mission to get the kick stage and strict satellite into position for payload deployment. The mission will be delivered first to a staging orbit where the kick stage will spend some time coasting around Earth before it can align itself on a circular path that meets Inspective's constellation requirements.
Yep, we have a single engine burn lined up for the kick stage to move out of that phasing orbit, which will take place around 40 minutes after its separation from the second stage. After that, we got a second Curie engine burn to line up the payload for release to its exact 552-kilometer target, all while moving at a nominal orbital velocity somewhere above 27,000 kilometers an hour.
But first up before that, of course, is the final separation event for this mission. Much like what we did with the first stage, we'll be shutting off the Rutherford engine with SECO, or second engine cutoff, before the kick stage is separated from stage 2 to set us off into a staging orbit for the mission. SECO should be coming up shortly now. Let's watch and listen.
Guidance is in terminal, 20 seconds remaining.
SECO confirmed.
Stage separation confirmed.
Nominal transfer achieved.
Beautifully done by the Rutherford engine with a nice clean shutdown on the second stage. And off goes the kick stage, now on its way to prepare for our 10th satellite deployment for Synspective's LEO constellation. We've got about 40 minutes or so in this coast phase of the mission before we come back to the kick stage.
During this coast, the kick stage's flight computer is continuously tracking position and velocity to refine its calculations for the optimal engine burn needed for its circularization and payload deployment. That's coming up at about T plus 53 minutes into flight and should last approximately 2.5 minutes. And then within an hour of liftoff, we'll be deploying the latest Strix satellite to orbit. Join us back here soon to see out the final moments of the mission.